Welcome everybody. So this week we'll continue working with cardinals. The next week we're gonna switch to ordinals, but we have a few more videos about cardinals, which are have some interesting proofs. Probably the most interesting proof we've seen so far. But before that, here's a small video about a small observation that is good to have. So, and it's the following, which probably most of you thought about before, I guess, doing the homework. If you have non-empty sets A and B, the following are equivalent. One is that there is a one-to-one function from A to B, and that's what we were denoting by A less than, it's dominated by B, right? It's a one-to-one function from A to B. A is dominated from B. And the other one is that it's an onto function from B to A backwards, okay? So essentially, if here is A and here is B, so one says there exists an one-to-one function f one-to-one from A to B, and we are saying that is the same thing as, let me move this a bit, as having an onto function that goes from A but onto everywhere onto in A, and those are the same things as, I mean, this is the same as A is dominated by B, so this is the same thing as saying that cardinality of A is less than or equal the cardinality of B. Okay, so you probably expected this to be true, and what is the reason why is this true? Because both of these are equivalent to saying that there exist functions f and g such that if you compose f with g, you get identity on A. So essentially, this picture up here, if this function going back is the red one is g going back, you get, and f is the blue one going there, f goes that way, g comes this way, then if you compose f, you get the identity of A, right? So you go, if you go from A, go and then come back to this composition, you get the identity in A, right? And then we proved this, I guess, in our second week, and essentially that is the theorem that we proved. I don't know if you guys remember, but it proves equivalent among these things, right? Having an inverse on the left was the same thing as being one-to-one. Having an inverse on the right was the same thing as being onto. And you use one or the other to prove these equivalence. Okay, so you can review that video if you want to see the proof of this. And essentially this makes sense, right? So if A is smaller than B, you can go to B and come back and get the identity and stay the same. But if B is bigger, I shouldn't be able to go to a smaller set and come back and get this identity again, right? So that's also a way of saying that cardinality of A is less than or equal the cardinality of B. Good. This uses the axiom of choice. If you guys remember, the first formulation of the axiom of choice came when we proved that theorem, that class, right? That was the first formulation of the axiom of choice that we needed to prove that theorem. Cool. Just a little comment to make. Pay attention to the details. Try to figure it out if everything works to make sense. See you guys in the next video.